you cannot neglect any length scale to begin with. And I illustrate that with this figure here. If you take a surface which you basically polish, it looks like a mirror. You see there's no roughness at all on it. But if you look at very high resolution, you will observe roughness, like I've shown you here. And then you have another surface here with much longer wavelength roughness and much higher amplitude roughness. One can show that if you push so much that the rubber make contact everywhere, and then you slide, then the contribution to the friction from this small wavelength roughness and the large wavelength roughness will be equally important. The only thing which will differ is that a small wavelength roughness will generate, if you slide at the same velocity, will generate higher frequencies during sliding. So it will appear, basically the short wavelength roughness will give you contribution to the friction which appear at lower velocity than the long wavelength roughness. But the magnitude is the same and the shape is basically the same. If the x is between x0 and lambda 0 is the same as the x between x1 and lambda 1. I will show you just in a moment how you can derive this lesson with background and calculation. I'll show that at the end of my lecture. So you cannot neglect any length scale to begin with. You need to include all length scales before you continue. This is how maybe the footprint will look like between a tire and a rubber. If you look at the system at the low of magnification or low magnification, you will observe a footprint here which is maybe 10 centimeters in both directions there. And here you observe some big aspirated contact area. But these big round asperities have smaller asperities on top of them. And if you magnify this contact area, you will observe smaller aspirated contact area. If you magnify this smaller aspirated contact area, it will break up into even smaller contact area because of this additional roughness which you will observe. And if you go down to the resolution or length scale of order micrometer, the contact area is only about 1 square centimeter between the tire and the road surface. And when you reach this length scale of about 1 square centimeter, with a contact area of order 1 square centimeter, then you will already start to build up so high stresses in the surface region of the tire that you start to break the bonds basically, and you start to get wear processes. And that's sort of what will cut off this. It doesn't make sense to look at even higher magnification because rubber is no longer rubber at higher magnification. So start to break the bonds in the rubber. This is one more very important thing I have to tell you before I show you some numerical reference. And that is that this dissipated energy in the rubber here will heat up the rubber. I told you the big rubber will deform, the bigger spirit will deform the rubber in a big volume element, but it will not put on so much energy within volumes. It will only get a little heating here. But close to this smaller spirit, you put much more energy within volume, so you will heat up the rubber much more here. And the shorter length scale you come to, the more you will heat up the rubber. And when you calculate rubber friction, you need to take into account this local heating, because I already told you before that the viscous properties are very sensitive to temperature. And basically, when the rubber gets hotter, it will dissipate less energy in the rubber. So this local heating will sort of reduce the contribution from short wavelength roughness. But this heating effect is only important when you slide at high enough velocity. If you slide at very low velocity, the temperature field can diffuse away, and you can neglect heating effects. This heating effect you will actually detect with infrared cameras. This is a tire which is moving a little to the, not braking, but in a curve. And you have always little slip in the curve, and you get some heating, and you get some hot spots. The colors here correspond to temperature higher than the surrounding. And even on the road, there will actually be heating. These are the equations which I derived for this situation. It depends on this is doing steady sliding. I have also equation that's sliding with non-steady sliding, but it's steady sliding. This is a friction coefficient. It depends on the power spectrum, which I introduced before. It depends on the integral part of the viscosity modulus. And it also depends on the absolute value of the viscosity modulus. So you have a set of equations here. Principal value of this is solved on the computer. I show you a reference here. This was some calculation I did for the film rubber, which is typically used for tire. Right? Here is low rate of sliding velocity, here is a kinetic friction coefficient, and this was a calculation without this local temperature increase and with the temperature increase. We call this flash temperature, this very local heating. You can see at very low velocities here, basically below 1 millimeters per second sliding velocity. You can forget about heating effects because the produced energy has time to diffuse away from the contact of the heat. But when you reach time velocity of say 1 meter per second, you have a drop in the friction by more than a factor of 2, which comes because of this heating up, which shifts the viscosity back at higher velocities, higher frequencies, and reduce the contribution of short wavelengths. This was another calculation I did. This is actually a thread block on the tire. It goes into the footprint, and then it after a very short time it leaves the footprint again. That's over here. And just when it comes into the footprint, it has not been sliding, and the rubber is basically cold. You get a very large effective friction coefficient here, 1.6. And then after a very short amount of sliding, you build up this temperature effect, flash temperature effect, and the friction drops to a much smaller value. And this happened was well known in tire industry, but they didn't know that it's a temperature effect. It's basically a kinetic effect. It's not a real. They take this as a static friction coefficient, but it's not a static friction coefficient. It's purely kinetic effect. Okay, now I come to my last thing, and that is thermal contact systems. Another problem of huge practical importance, and what I again applied my contact mechanics theory. I will tell you about thermal contact systems, but there is also an electric contact system, which can be handled in a very similar way as thermal contact systems. So here we have two blocks of materials. We have some rough interface. We have them squeezed together, and we heat up this surface here, and this is kept at a lower temperature. And then you will have a heat current which flow here, and when it comes to the interface, it has to go over here in some way, and it can go through the area of low contact, or it can diffuse. If there's gas here, it can diffuse in between here and the gas, or whatever. But anyway, close to the interface, you will have a very complicated temperature field. Here the temperature will be almost constant, but close to the interface, it will vary very rapidly when you go over the surface here. And people have introduced something they call heat transfer coefficient, and they basically say that these heat currents which flow here, and it must be the same everywhere. If you have a steady state situation, the total heat current must be the same in all cross sections. That heat current at the interface here will be related to the temperature drop in the way I indicated here. This is called the heat transfer coefficient. And the temperature drop knob, in order for that to be well defined, you cannot look at temperature right at the interface because it is very different there compared to there. You need to go some distance away from the interface, determined basically by, say, the wavelength of this roughness or the distance between such contact points. If you do that, then you will have a temperature profile which is almost constant here and almost constant there. And it will be higher here and smaller there. And in that way, you have to define this heat transfer coefficient. So here is shown how the temperature actually works. When you go up here, it drops linearly. Come close to the interface here, it drops very much over a very short distance. So in this kind of picture here, you put this lambda equal to 0. We assume it is an instantaneous drop, but in reality, it is over some distance lambda here. And then again, it depends linearly on when you go away from that interface up to that surface. So the basic problem is how to calculate this. And this one is of very great importance. For example, in the beginning you heard many presentations about graphene. And we have done calculation for graphene also. And graphene, we want to make transistors out of graphene, for example. You have graphene, you have the substrate, absorbent substrate, usually silicon dioxide layer. And then you attach metal electrodes here, and you apply voltage and drive a big current for here. When you drive a big current for here, you will heat up this graphene layer. And if you would have no energy transfer from the graphene to the substrate, the system will finally disintegrate. So the very important quantity is the energy transfer from the graphene to the substrate, which again is determined by heat transfer coefficient. And so we work on that volume too. But here I'm going to speak only about the case where you have two blocks, not the main one and the surface. This figure illustrates all possible mechanisms. So if you have contact between the solids in some areas, you can have phonons propagating from one side to another side. Or lattice waves basically go from one side to another side. Or electrons, if it's metals, you could also have electrons which go from one side to another side. And that will lead to energy transfer from one side to another side, from the hotter to the colder side. In the non-contact reading, you can have blackbody radiation. You know that a hot solid emit more radiation than a colder solid. So you will have heat transfer from this side to that side, coming from basically blackbody radiation. If you have a gas in between here, you can have diffusion of heat in the gas. So the gas gets hotter over here and colder over there, and you will have a heat transfer. And if the gas, if this spacing is very small, if it's smaller than the mean free path of the gas molecules in the gas, then you will have even ballistic transfer of energy. So one molecule comes here, hit into that hot surface, pick up some energy, just move up here without hitting into other molecules, and transfer some of this energy picked up, and which we call ballistic energy transfer. That becomes important when the mean free path becomes, the separation becomes smaller than the mean free path for the molecules in the gas. And finally, in many situations, we have also meniscus, like I told you before. And they, in some sense, will enhance the contact area, and you can have effective transfer of energy, diffusion of energy from one side to another side. So this liquid meniscus. Also, in some cases, the dominant mechanism. And you can see that all these processes act in parallel. So in the first approximation, the total heat transfer coefficient will just be the sum of all these different contributions. And often, one of them dominates very much over the other one, and then you can forget over the other one and just include one of them. This is the result of my contact mechanics theory. The heat transfer coefficient, which comes because of the area of real contact, is given by this equation which is shown here. P0 is a squeezing pressure. P star is the effective elastic modulusine, P star over there. U0 is this length parameter, which ended in the relation between the contact pressure and the interface of separation. And yeah, that's all the parameters. And kappa is an effective heat conductivity. So this is the heat conductivity. One of this effective heat conductivity is the sum of one of the heat conductivities of the two different materials involved. Good. I will not say more than that. There is some interesting aspect here, but I will not. I will only say that this heat transfer coefficient is determined by the long wavelength hardness. It does not depend on short wavelength hardness. It's basically only determined by the long wavelength hardness. So that's what determines this U0. It depends only on the long wavelength hardness. So you don't need to know all the short wavelength hardness in order to calculate this heat transfer coefficient. And that was illustrated here. To calculate the heat transfer coefficient, you don't need to know what the contact looks like at the highest magnification. It's enough to know what it looks like at a much lower magnification. And that's good because these magnifications get very complicated. Then we have the heat transfer via the surrounding gas, and that takes this form which is shown here. This is the heat conductivity of the gas. This is the temperature difference, and here is local separation here at some point, and gamma is the mean free path for a molecule in the gas phase, and A is the number of order unity. So you can see that if the mean free path becomes smaller than the mean free path, you can neglect this D here, and that means you can neglect the heat diffusion, and you have only this ballistic energy transfer, which is determined by this gamma here. And in calculating now this heat transfer coefficient which comes out of this contribution from the gas, you have to average this quantity over the whole interface. So you have to average D plus gamma over the whole interface, and that you can calculate using my contact mechanics theory. Basically, what happens is this probability distribution in phase of separations. Okay, so again, we need to propose Lawrence did some experiment to test my predictions of of the theory. And this is again a simple experiment to have a box with water which we heat up, and we mix it to have a uniform temperature here. Here we have a copper surface with roughness, here we have another copper surface, and then here in between we have silicon rubber layer. And then we just heat up this and we look at the temperature increase down in that fluid. And from the temperature increase here, we can obtain the heat flow through the interface. And we assume that we have good thermal isolation, so there is no loss of energy to the sun. And we did this with a few different surfaces. These are three different rough surfaces with different power spectra, three different copper surfaces. You don't need to know the details of that. That too, and I will only show you here the results of the experiment compared to the theory prediction. And here is shown the temperature increase, a function of time. And we have three different surfaces, 1, 2, and 3, and we have also one flat surface. And all these small dots is Messier data, and the solid lines here is what the theory predicts. And again, in this calculation, there is no fitting parameter. We take the Messier surface roughness power spectra, and all the other parameters are also known. And it's not perfect agreement, but it's not very far away. And this was another conversion where we use two different squeezing pressures. So the low squeezing pressure and the higher squeezing pressure. And with the higher squeezing pressure, you get more contact and more heat transfer, and you can see the temperature is increasing faster in the lower container when you have high contact pressure. Again, the agreement is not perfect, but it's not that either. I want to say a few words about the radioactive contribution. So now we assume there is no gas in between here. We don't consider this either. We have only the black body radiation now. And this is a very interesting theoretical problem, which is a very hot topic right now. Because you know that if you have surface separated by large distance, then you have so-called Stefan Boltzmann law for energy radiation, which tells that the energy radiation goes at temperature to the 4, if I recall right. And this is due to emission of real photons which propagate from this solid up to the other solid and get absorbed here. But if two surfaces are very close together, you don't need to emit real photons. You can have evanescent waves, because when you have charge fluctuation inside the material, you get not only emission of real photons, but you get evanescent waves, which decay away from the surface. And if the surface separation is small enough, this decaying electromagnetic wave will penetrate into the upper solid, and it can transfer energy via this electric field into the upper solid. And this effect here becomes a very short separation, like maybe 10 nanometers, so it can be a million times stronger than the prediction of emission of real photons. And this is the mechanism which is illustrated in this figure here. There is some thermal fluctuation in the charge distribution here, which gives rise to temporal dipoles. And those dipoles are surrounded by some electric field, which penetrate into this material here and can make excitations here. And if these are metals, for example, there's another picture of having it. You have such a fluting dipole, you get basically when an electron above the primary surface falls into a hole below the primary surface, and that fluting electric field from that can excite an electron from below the primary surface to above the primary surface in the lower material. So this is a microscopic picture of how this is happening. And this figure just summarizes what I told you, that if you use Stefan Boltzmann law, which means you have large separation between the surfaces, then the heat transfer goes like temperature to the 4. And since you can emit radiation in both solids, you have to make a difference between the temperature of the two solids. But this is not a very effective heat transfer mechanism. So at room temperature, it will give you 6 watt per square meter Kelvin for the heat transfer coefficient. Now, at a very short separation, I told you that this evanescent electromagnetic wave can start to become important. And in that case, we did a calculation here where the material is silicon dioxide, because it's typically used for these devices involved in this experiment. And you have separation of 1 nanometer, so it's very short separation, and room temperature. You see you get a number which is almost 1 million times larger than over here. And in fact, there is a very recent experiment where people have measured this effect. This is when they have a ball and a flat, and you heat up the ball, and you can measure or you heat up the substrate, and you can measure the energy transfer to the ball. And you can do this in vacuum, and you can measure the temperature up here. And people have found that the heat flux between the solids scales like 1 over the distance between them. And that's exactly what this theory involving the elements and waves are predicting. And even the coefficient in front of this power law here is in agreement with what one can calculate from theory. Yeah, I think we have applied this theory to MEMS devices, but I think I will skip that, and I will skip this theory because this I'm getting tired. But I wanted to show you this derivation. That's my last thing. So this is a derivation of this, how you can show with back of envelope calculation that a long wavelength roughness with large amplitude will contribute to the same total Hubble fraction as a short wavelength roughness with smaller amplitude if the ratio between the amplitude and the wavelength are the same. We assume that this ratio is the same. So this is again one of these very small back of envelope calculations, but which is very important and which you would like to do before you do the big calculation. So we assume that we have applied such an exclusive bicycle that the Hubble is in contact everywhere in this sinus profile here. And first I want to calculate the elastic energy which is stored up here in order to deform, to come into contact. And that elastic, if you have like a sinus wave here, you will have this number of regions where you have to deform the Hubble into the cavities. You will have one here, you will have one there, one over there. So the total surface area divided by the lambda square here will give you the number of regions where you have to push in the Hubble. And in each time you have to deform the Hubble over a volume element, which is order lambda cubed. Because I told you that in order to deform something, if you deform something, or you have some stress over a region of lambda, of order lambda here, it will also extend into the solid, the distance of order lambda. So the volume which is deformed is of order lambda cubed, in each such wavelength. And then the energy per unit, plastic energy stored per unit volume is the stress times the strain. And the stress again divided like the elastic modulus times the strain, so you get the strain square. And the strain is h over lambda. That's the typical strain you will have in this volume. And then you just multiply together two things, you end up with this expression for the total elastic energy which is stored up here. Surface area times elastic modulus times h square over lambda. Now if you slide some distance L, then you will have L over lambda pulsating deformations of the Hubble. And now if one assumes that in each such pulsating deformation, some fraction, which I call epsilon here, of this elastic energy which we need to deform the Hubble to fill up the cavity, if that is lost into heat, or dissipated into heat, if you assume that, then you get the total dissipated energy when we slide distance L, given by the number of pulsating deformations, times this epsilon, which is a number smaller than 1, times this energy U here. And if you just plug in the expression of U, which I got there, you get this expression, and here you see you get lambda squared down, and then h squared up. So you can see that as long as h over lambda is the same, you will have the same amount of energy dissipated, independent of how big this roughness is, independent of the wavelength. You only tell this number the same. And one can even extend this direction a little and make sure that this epsilon here is related to tangent delta. But it's not important here. Okay. Okay, yeah.
Okay, when you have these results of heat transfer, which show a good agreement with experiment, so I just wonder, did you just for illustration try also just the ideal contact? I mean, what significance does it make your correction considering the rough surfaces in transfer? Would it be like completely different?
We did, in order to have a well-defined product, we choose rubber because we know how to work with rubber. But actually, in fact, most of the heat resistance in our problem came from heat diffusion through the rubber layer. It does not come from what happened right at the interface. It comes from the heat diffusion through the rubber layer. That's why you saw that all the curves we showed was rather similar. There was not so big difference between them. And that's because most of the heat resistance comes from heat diffusion through the rubber film. So we would like to do an experiment with a thinner rubber film, but the rubber film cannot be thinner than the roughness, because then it doesn't deform like an infinite solid anymore. So actually, even having a flat surface in this situation would make only having a flat surface with perfect contact would only make a relatively small change to the heat. But that's in this particular situation. If you have two metals in contact, two good conductors in contact, the situation is completely different because there you don't have so much heat resistance as you will have with this other film integrate. But we have not done experiment with two metals. Because it has additional complications.
So your alpha coefficient is magnitude dependent. So depending on which scale you are
No.
Because you said the radiation transfer is.
This is heat transfer quotient. Is heat transfer. It relates the current to the temperature difference. So to get the total heat transfer, you have to multiply it with the average surface area, nominal surface area. This will give you the heat energy per unit volume going from one solid, energy per unit time going from one solid to another solid. So this would be given by this expression.
Yeah, but I mean, for the radiation,
Yeah.
you had 6 watt for something and 1 million.
Yeah.
So at two different scales.
Yeah.
But you cannot consider 1 million at the larger scale. Of course, you have to consider the scaling law at T to 4.
Yes, this was at the room temperature. So if you go to higher temperature, finally the blackbody radiation increased faster than this non-radioactive contribution. But at nanometer separation, you can never go. You have to go to so high temperature that the materials are melted before even they are close to each other. So and most of these applications are not so far away from room temperature.
So basically, the results you showed, there is no radiation contribution.
In this calculation, in the calculation with the silicon, with the rubber film, the measurement which Boris Laws did, you can neglect this because the separation is too large. We have typical micrometer separation, not nanometer separation. This non-radioactive contribution becomes important only when we go to things like not a smooth surface like in MEMS devices and things like that.
Can you turn the slide with the derivation?
Oh, with the derivation. With that?
Yeah, you use the linear elastic stress strain relation.
Yes.
Even though it's a rubber.
Yes.
Why not hyperelastic or something like that?
Because this is, I want to show you something simple, I don't want to show you something complicated. If you look at real rubber, particular field rubber, it's rather non-linear. And what we do in all our application, because all the theories are based on linear viscoelastic material, what we do is that we take the viscoelastic modulus, measure it rather large strain. It's the best we can do. In that way we build in some of these non-linear properties. Because the real strain in, for example, tire application is of order, typically can be of order 100% strain in the aspect contact rate. So we have tested this. We have measured viscoelastic modulus with different strain amplitude, and we have found that only if you use viscoelastic modulus measured at high strain are you able to get reasonably good results. So it's not, as you say, it's not a linear viscoelastic material, it's really non-linear, but putting in both the non-linearity and the frequency dependence is almost impossible topic. Even to describe it is almost impossible, and then in addition you have to put it into the theory and it becomes impossible.
Even if you try to solve numerically the problem?
If I try to
solve numerically?
There's a lot of people who try to solve this numerically, and everybody will fail. With finite element methods and all kind of, they can maybe do one sinus profile. Even that they are not doing properly correct. So roughness on one single landscape. That's what, because it's complicated when you have viscoelastic material. And in reality you need to account for many decades in landscape. It becomes impossible. Even the elastic contact mechanics, you cannot solve properly with more than 2 decades or between 2 and 3 decades in landscape. With the system you cannot solve it. It's not, maybe if you go to the computer you can do it a little bit, but not very much.
Okay, thank you very much.